what I'm trying to do is trying to leverage the power of analogy to try to improve mathematical outcomes. What you are going to see is an effort to uh, try to improve the achievement of, to stimulate children early mathematical competences. So let me, well, in Latin America, we have a lot of problems with mathematical performance and also mathematical anxiety. And I think one of the problems is the traditional form of teaching, right? Um, so what is the idea that I wanted to apply? Um, the idea, some of the research of the analogy community is that well-crafted and adequate analogies can be used productively to enhance education and especially mathematical education. So here we see some work from Richland, Lindsay Richland, Kate Holiak, and other colleagues that try to measure how well teachers applied analogies. They show that countries that whose teachers were more able to use analogy in classroom also have better performance at teams in teams the standardized proofs. So what they provide evidence for is that, for example, teachers in Japan were more able to put more analogies. The source and the target of the analogies were more visible together, and they, constructed more carefully the analogy between one concept, mathematical concept, and some everyday experience, like, for example, plates for equations and other analogies that are useful in education. So one of the theoretical support for the work I'm going to present is this kind of research. There is a lot of evidence in this area about the usefulness of analogy in education, but Nina Sims and Listen Richards have also brought some challenges that, ban to apply analogy in education. There are especially two: learners might not recognize the possibility of making an analogy, even when there is available relational correspondences. So learners just are not able to carry the structural mapping from one situation to another. And the other is that high processing demands of analogy and higher order thinking maybe is too much for students. So one of the key issues that they state is the teaching higher order thinking across mathematics, science, and history is to conceptualize learning as developing and manipulating relational systems. So one of the more important things is about relational systems. I'm going to show later some way of understanding analogy in more, in not a classical way. The other theoretical background for this research is we know analogy works in classrooms, but also other thing that has been shown promises is spatial thinking. So for example, Nora Newcomb states that even a little shift in the spatial abilities of children would multiply the number of people that could go to make, for example, engineers or scientific, because spatial thinking or spatial abilities has been shown to have a lot, very strong effects on learning. And she draws two strategies. One is um, enhance students' spatial skills early in life or less prior to instruction, give them more spatial abilities. And the other strategy is use, basically take the curriculum and make these, integrate in it the spatial abilities. So these are the two things that I think it's important for this research. So I'm going to show an example of how we can leverage those two theoretical sources into an intervention. Um, this intervention is based in the work of Robert Siegler and Greta Ramani. They used these two kind of game boards. The thing is not really, the thing that they show is that this board at the left make children to learn numbers, and this board at the right, children playing this game board just don't learn numbers. So the very easy answer is of course there are numbers printed on here, and so it's kind of natural that they learn numbers. But they also give this another study in which they say, okay, let's do this game that is a circular game, and let's print numbers on it. And they showed that the numbered game, the one that is linear and also has the number printed on them, produces learning, while this other one doesn't produce learning. So the idea is a little bit more, the answer why children learn numbers with this game is a little bit more complex than just because they have numbers. So one of the ideas is that in our more basic cognitive system, we have magnitude representations. We have magnitude representations, and the idea of this research is try to leverage these magnitude representations to produce learning. The first problem that we have is trying to represent, for example, the numbers in the classical structure mapping representation, in which we have the numbers like here, 1, 2, 3, 4, 5, 6. But for example, the relation of successor, the 2 is the successor of 1. We need a node for doing that, and another one for the 3 is the successor to 2, and so on. We have at least 9 nodes for the successor relationship. But when we want to, represent the lesser than relationship, so we had the combinatory explodes. So we have a lot of nodes here trying to represent the lesser than relationship. So actually, for representing the numbers, I would need hundreds of nodes to represent that structure. That's kind of a difficulty for making the analysis that we need. So this is work based on Holiak, Kate Holiak. I think I found a paper talking about this of 1980 or something like this. It's very old research, but I think it is useful. So the idea is this is when I applied category theory. It's a formal mathematical theory, but it's I'm going to try to give just the enough details so the analysis can be understood. So here we have a kind of a thing I call domain, which is the representation of a board that is just spatial. If you see here, we have 10 10 boxes, 10 boxes, and they have no numbers because they are not numbers, they are just boxes, and but they have a structure. They have a structure in which one box is to the side to the other box, and there is certain perceptual distance between two boxes. For example, these two tokens here are separated by a number of boxes, and we can walk through this path and get from one box to another box. So if you see here, we can use variables. This is kind of like mathematics, and evaluate these sentences. For example, to say if X and Y take these two boxes, these spatial boxes, I can say, wait, Y is to the right of X. In this case, I think it is false. Depends where do you see it. What is the walking distance? And I can give a kind of magnitude as a response. And I can say, well, if I am in X, which one is the box that I obtain if I go one step to the right, for example. These are some structures that these simple 10 boxes are endowed with. And the thing that I think is important is this structure, we are built with this structure because children can navigate the space. Children can walk from one place to another one. They can understand these things really, really easy. But let's see what happened. So in this case, I have represented the domain, a domain. Do you remember I needed like hundreds of nodes to represent a similar structure, but with this, I have the same representation. And now I need, this is kind of a perceptual representation. And this other one is the same for numbers, but these numbers are abstract. No one has seen a number in the street or something like this, This number is just a symbol we use, but what makes this set a number set is the relations that there are between those symbols. So when you have these two representations, to the left, the game board, and to the right, the numbers, this is an abstract construction. We can understand what is the analogy between those representations. For example, y to the right of x corresponds to y is greater than x. The distance between x and y, aquí, this is a magnitude distance. And here to the right is a numeric number distance, And the one that is walk one step to the right direction, it is the successor of numbers. So this is a formalism, and so you can say this is analogy because this diagram commutes, and that this diagram commutes means that whatever evaluation you do of each of those symbols that are above here, for example, let's see this, a step to right x. X evaluates to the first box, and h relates the first box with the first number, and the other h evaluates a step to the right x with successor of x. And like the evaluation here goes to the first box, this goes to the number one. So if you go the evaluation in this direction, like down and to the right, is the same to going to the right and then down. And you can do it with every pair, every symbol here. And when you have for every symbol and every evaluation, you say, okay, I have an analogy, and it is a representation that it's more difficult to do with the classical structure nodes representation. So this is the idea, and so you have for you can separate each one of those. And so when you give a step in the board game, you is the same like going presenting the successor in the number domain. And the same when you see a distance in the board game, you can associate it to a number distance. So this idea, this is the one. What I am going to show is an educational intervention that use those ideas to make the argument that children's representation of numbers can be built on spatial representations. So what do we do now is we devise a kind of intervention. I'm going to show you a little bit later about this intervention. But the thing is, we kind of made this huge board game. Well, it is like a street game, this huge game in which the experimenter was explaining to children about what happened with these two characters here. And the idea is that in each explanation, he was going to explain a concept and trying to leverage the analogy. For example, when they see this picture here, or this scene here, they say, okay, look, the rabbit is ahead. So which is winning the race? So winning the race in here is which is in the greater number. So the children will observe the space and notice that the rabbit has gotten ahead on the race. And then the experimenter will say, okay, the rabbit is in the number 8, the turtle is in the number 5, and so that is why this is winning. So they are kind of blending the two worlds, the spatial world and the number world, and then children will play with this kind of intervention. So each one of the structure that you see in the analysis was integrated here in some way. So what was the experiment? It was a controlled school intervention. There was 77 children. Actually, there were a little bit more, but some children were out of the study because they got sick. There was an active control of 31 children. The active control have the same exact material and the same exact like a script, but there were no numbers, but figures like a house and a tree and an airplane and things like this. The other two groups are like this. The one group is this group here, like in this side of the room, and the other group is this one here in this side of the room. In the other side of the room, we have the idea that they will learn a little bit different than those, even when they share the same classroom, the same materials, the same teacher, they had different patterns of learning, and it helped us to show that space actually is integrated into number representations. So what was the idea? If you notice, children in this side of the room see the numbers ordered from left to right. So numbers go like in the natural direction from 0, 1, 2, 3, but from left to right. And children in the other side of the room see numbers from right to left. So they see like in the order of negative numbers. So even when they were in the same classroom, they were with a little bit different perspective. We measure some measures, we measure some performance measures, like children counting correctly up to 10. Um, in this case, children in the same in the two later groups were grouped into the class called number group. So they are here treated like one only group, and the control condition was in another is this data, right? So children in the experimental group effectively learning to count it more, and also they were able to identify number symbols better than the control group. In regard to the comparison, numeral comparison, that is, you show them two symbols like 3 and 7, and they have to decide which is the greater. We have like mixed results. This is not really significant between the difference. But the interesting one is this one. We have here the three groups of children. This is the control condition. This is the children who see the numbers in the direction from right to left. And this is children who see numbers in the direction from left to right. And the only group who have significant gains were this group here. So why this group has a significant difference? It has to do with the way we measure this performance measure. This is the number line estimation task. What is this task? You have a number line. You have 0 in the left part of the screen, 10 in the left part of in the right part of the screen, and you show him a number and say, okay, where it is this number? And they have to show where in the middle of on the line is this number. So children in this side of the room were used to this representation from left to right. And it is possible that for these children in the other side of the room, they have a lot more work to do, more cognitive load, because they have to transform what they saw in the room to like rotation, like to perform a rotation to answer this question. So it is more difficult for them, this task, and this explains the results. But the important thing is it shows that the way you train children using space matters, because the representation of numbers in children become integrated with the spatial representation. So this is the key message I want to give, right? So this was the idea of this research, trying to understand that you can leverage spatial magnitude representations and make an analogy to create a new representation of certain abstract concept. That's the main idea. Then number representation in these children integrated a spatial reference, such as, for example, number 1 is to the left of number 2, for example. And one of the things was at the beginning of this research, we like read a paper of Lecori and Kari, who trying to explain how is that numbers are learned. And one of the mechanisms was association. But for example, these kind of results go against mechanism of associations, but support kind of mechanism like analogy to build the representations of numbers. This is the team that helped me to make this kind of research. I want to show you just a little bit. This is not the actual experimental sessions, but some kind of, you know, we have done some. I want to. I don't know why I can't.
Eso, Sofi, bueno, muy bien, Sofi. Vamos, Sofi. Vamos, ponle, para allá, para allá. Eso. Muy bien. Niños, tienen que estar atentos, ¿verdad?
Sí, porque algunos dicen el número y están viendo mariposas.
Entonces, conejo, rápido, saltó del 2 al número.
¡Chapo!
Del 2 al... Vamos a dar un punto al que diga el número más fuerte, ¿ya? Ya. Va a pasar el conejo del 2 al número... Muy bien. El conejo gana otro punto y pasa del 3 al... Muy
Pero no
bien.
es gritar, es decir el número.
La tortuga...
So this is we have done some experience with board games too.
No, pues estás comiéndote todas las tarjetas de lechuga y no se puede comer todas.
¡Ay, mamá!
Well, and also the same analysis with fractions. We can do the same kind of analysis with fractions, but now we have like good blocks that you can put together or compare, and you can make the game so you can call attention to those analogies between these blocks and the fractional numbers. And we have a pilot we were going to test but just pandemic goes in and we just have the pilot study. But in the pilot, we got some encouraging results in games. So the control, it's a very little, like 42 participants or something. In the control, they didn't learn anything, and in the experimental group, we observed some significant gains of knowledge. And well, the time is almost gone, but I wanted to show you what I'm going to work, what I'm working now. We are doing the same, but trying to do material to foster early mathematical abilities. So for example, we have some kind of map, and we have no time to test yet, but children have to navigate this map so they can identify spatial orientation, pattern creation. So they have different patterns and try to get them. And all this is done with the same methodology of analyzing the analogy that we're trying to create between an abstract concept and a space. This is the idea that I'm trying to carry forward. I think I am in the time, so I'm going to stop here and thank you so much for hearing me out.